thinks about it, he worries about it. When Jeff wrote on his slide, properly discontinuously, we don't like that, Jeff. We don't like that. When people say Teichmuller space, do we really mean Fricka space? So we were, and Bill worries about this. In fact, crooked planes, you saw crooked planes, Jeff just showed us some crooked planes. He named them. We talk about stems and wings. And when we were in Dalhousie University with Lisa, our next speaker, we were talking about crooked planes. We were telling her about, oh, crooked planes have the stems and the wings. She looked at us, she looked concerned for us. She was a little worried about Bill's naming system. Because a stem is from a flower. It's a plant. And wings, butterflies. They're an animal. Bill, I'm a little worried about that. She's shaking me to the core. I'm a little upset. Anyway, so I hope you're going to shake us to the core on something else, on the character of variety in genus 2. Lisa Jeffrey, who is a fellow of the Royal Society of Canada.
Thank you for the very generous introduction. I didn't remember that about the plants and the wings. I first met Bill in 1988-89 when I was a first-year research student in Oxford, and Bill was on sabbatical there. There were many photographs of, Bill reminded me of this a couple of days ago, there were many photographs of my supervisor, Michael Attia, in the Maths Institute. And Sir Michael is a knight. Bill's son, Evan, was also visiting, much younger now. He's doing photography younger in this conference. Bill reminded me that Evan asked, well, was there a photograph of Sir Michael on a horse? Much later, Bill was the go-to person for the computer system at the Park City Mathematics Institute summer 1991 after I finished my degree. And more recently, Bill has visited Canada fairly regularly and doesn't seem to be deterred by the inclement weather, although given the thunderstorm on Tuesday and today's rain, I think maybe the score is even. Anyway, happy birthday, Bill. A student of Bill's, former student of Bill's, Eugene Chia, and my former student, Matt Pope, and Hua Dang-Rin, who has just finished his undergraduate degree at University of Toronto and is going to physics graduate school. And we are working on character varieties, which have appeared in Nigel's talk yesterday and Anna Bienhart's talk. A two-manifold G will mean normally group elements, so I'll call the genus K. And that big G is the compactly grouped. In this talk, G is SU2. So we have the representation variety. This is also appeared in yesterday's talk. Just the space of representations from a fundamental group of the genus K, two-manifold, into the group. These things are just elements of SU3, you can say that. And this symbol means not as in most talks, the lead bracket means the commutator. So we'll insist that the product of commutators is equal to the identity. Those are the representations of the fundamental group of the genus K surface into SU2. character variety is the same object when you have taken the quotient by G under conjugation. So in genus 2, this just means that you have 4 elements of SU2, and the commutator of the first 2 of them is the inverse of the commutator of the second pair of them. And then you take the quotient by conjugation. Now, Narasimhan and Ramanan studied this object in 1969 from an algebraic point of view, and they showed that this object is actually smooth, and it's homeomorphic to complex projective 3 space. Their proof uses algebraic geometry methods rather than symplectic methods. Now, CP3 is a toric manifold. It has the standard Hamiltonian action of U1 cubed, and its moment polytope is a tetrahedron. This reminded us of something familiar from Bill Goldman's work, 1986. This paper is called Invariant Functions. He constructed Hamiltonian flows of certain functions on the character varieties. I misspeak. You don't actually need a pen to decomposition yet. If you take any simple closed curve, C, on the 2 manifold, then it will give rise to a function which is just takes a representation and sends it to the trace of where the shouldn't probably even introduce the word polynomial at this point. I just mean where the representation sends the loop around this curve C. Once you've picked your baseline. There's a trace, so it doesn't matter what it is. So Bill studied the Hamiltonian flows of these functions. He constructed them. I should maybe draw a picture. It's not that hard to draw a genus 2 surface. Okay, so a separating curve means a curve which, if you cut around it, then this decomposes into 2 components. So this would be a separating curve. And what this Hamiltonian flow is, according to Bill, is you take your representation and you conjugate by an element which is in SU2, but is I probably should have used instead of using a notation that suggested that you have something in U1, I probably should have said that. For EBICT, I mean the diagonal matrix with eigenvalues. conjugate by that, that's the Hamiltonian flow. If you have a non-separating curve, such as this one, you have that along that, then you still have that on there. Then PVIC, P means the same thing. You just write multiply instead of conjugate. That's the Hamiltonian. Another way of saying this is the description that appears in my work with Jonathan Weissman on four Somersault orbits, number 93. Suppose you have your surface, and it really doesn't matter whether the curve is separating or non-separating. Suppose you cut along the curve, then there will be two boundary components. So let's say I'll call it C plus and representations of the fundamental group of two manifolds up to conjugation are the same thing as gauge equivalence classes of flat connection via Hamiltonian. So if we instead work with a flat connection on the surface, then what Bill's Hamiltonian flow does is to take your flat connection and conjugate it by a gauge transformation, which is equal to the identity on one boundary component. So on C plus, the gauge transformation is equal to the identity, and on C minus, it's equal to not the identity, but something that is in the stabilizer of the restriction of the connection to C. So when you gauge transform, the restrictions of the gauge transformed connection are the same on C plus and C minus because you chose this to be in the state. You chose this thing to be in the stabilizer of the stabilizer restriction of the connection to C. But the gauge transformation doesn't glue back together to form a gauge transformation on the closed surface. So you get something non-trivial happening on flat connections on gauge. And that is how you get the Hamiltonian flow of the character. So that's how Jonathan and Weissman and I thought about Bill's Hamiltonian flows. Bill proved that if you have two disjoint simple closed curves in the Riemann surface in the two manifold, then the corresponding Hamiltonian flows commute. So for these two that I want the Hamiltonian flows commute. And Jonathan Weissman and I observed that if instead of if instead of using trace of all C, we used all C instead, so that just means, I think I wrote it down on the previous slide. What Bill was using was tracing. So we observed that this function is the Hamiltonian, is the moment map for a Hamiltonian S1 action where it's defined. Now, it's not defined when rho of the loop is in the center of S. Because Bill's prescription for the Hamiltonian flow says you have to take a maximal torus, and if rho of C is in the rho is in the center of the group, then you can't. There's no way to pick a maximal torus. The center of SU2 is in all the maximal torus. So you can't. There are points where you can't define the Hamiltonian flow, but otherwise you can, and this is the flow. So Bill's original description, by the way, is defined everywhere on this, everywhere on the term. So the Hamiltonian flows that John Weitzman and I used are defined only when we don't use sample elements. So okay, so what could be the moment polytope of these Hamiltonian of the Hamiltonian these Hamiltonian flows? Suppose you take a Pence decomposition of the genus to surface. There are two Pence decompositions. One I've actually drawn the. So one Pence decomposition is this one. Let's draw it again. Glue the boundary nodes to be as I'm thinking the XY plane, and then reflect the whole thing in the XY plane. So it turns out that the image of these moment maps is also a tensor. There should be a comma there between 0 and pi. So that looks like this. It's the tetrahedron that is the convex hull of these vertices. It's actually not exactly, not the same as the tetrahedron for the Newton polytope for the CP3, which is the convex hull of these vertices. You can't get, short varieties are the same up to isomorphism if there is an isomorphism between them, between the polytopes by an element of SL2 set. This doesn't happen. Obviously, you can map. You can map the you get a map between tetrahedra just by mapping the vertices, set of vertices to each other, but it's not in SL2 set. So this is what this tetrahedron looks like. I wrote down the vertices on this slide. And T1, T2, T3, those go from 0 to pi, and the inequalities are very
Lisa?
Yes.
Can I ask you what happens if you take a different pair of pans decomposition?
Yeah,
because there is a second one.
Okay, the other pens, if you do not get, the other pens decomposition is where you have the boundaries of the. So you take him. Yeah, that's. Yeah, the other pens decomposition is in fact this one. So you just take one pair of pens, glue the ends together so you have a one-fold torus, and then that one, instead of having a tetrahedron, you get a pyramid. And the volume of the pyramid has to be the same as the volume of the tetrahedron. The volume is not you'll be able to determine for either pens decomposition. That's going to be independent. So what Nanko, Eugene, and Tuan and I thought we could do is use Douster-Mutt's theorem. This paper is called Convexity and Tightness of polyhedra. The result is that if you have a symplectic manifold with an anti-symplectic involution, those were introduced in Nigel Hitchens yesterday, and you also have a Hamiltonian action of a torus of half dimension compatible with the involution. Then the fixed point set of the involution is a Lagrangian submanifold. And furthermore, the image of the fixed point set under the moment map is the same as the image of the whole manifold under the moment map. By the way, it doesn't follow that the moment map maps the fixed point set, the Lagrangian submanifold, bijectively to the monopole. You'll see even CP3 is an example where it's not a bijection. You'll see why. Here the standard U1 action is U1 cubed action is compatible with the involution. And the fixed point set of the involution is R2. So what happens with M2, this thing? This also has an anti-symplectic involution, which is just you switch the pairs of points. You switch G1, H1, G2, H2 with G2, H2, G1, H2. The fixed point set is rather complicated. It does include G cross. You would expect that if G1 is equal to G2 and H1 is equal to H2, that is that is obviously a fixed point. But you also have to account for the fact, what if they only become equal after conjugation? So the fixed point set contains the set G cross G mod G, but that's not everything. I wrote down N1 and N2, and those are not disjoint. The fixed point set is connected, and it's actually homeomorphic to RP3. This object, G cross G mod G, appears in a paper by Bill Goldman in 1979. Pillow space. It's not RP. It's not RP3, but related. As I mentioned, the restriction of the moment map to the fixed point set of the evolution is not a bijective correspondence. For CP3, the reason is that the restriction of the moment map to RP3 is 1-to-1 on the vertices of the tetrahedron. The reason is you have these tuples of 4 numbers that you're dividing out. You should set the sum of squares to be equal to 1. If all of the numbers is a projective space, so you are dividing by multiplication by scalars. Restriction, this map is 1-to-1 on vertices, points where 3 of the 4 coordinates are equal to 0, and 2-to-1 on the edges, 4-to-1 on the faces, only 1 of the coordinates is 0, and 8-to-1 when no coordinates is 0.
Did you consider using other involutions? Because there's other involutions compatible with the picture.
Yeah, we did this one seemed we thought, we hoped would be clear. I would like to talk to you later if you have other suggestions. So the torus section is well defined on the pre-image of the interior of the tetrahedron. And we can construct a bijective map from the pre-image of the tetrahedron to an open dense set in CP3. Because there are 2 tetrahedrons. The way you do this is to identify the 2 Lagrangian submanifolds, the fixed point sets of the evolutions, and to use the Hamiltonian U1 cubed actions to identify orbits of points in these Lagrangian submanifolds. But this procedure breaks down on the boundary of the fixed point sets of the anti-symplectic evolutions. So it breaks down on those copies of ours. So the region where this map is not defined involves, so first of all, the pre-images, what happens on the pre-images of the vertices. So points that are in the center. Then the pre-image is actually G cross G mod G. So the dimension of the pre-image is 3, and what I mean by excess is the difference between the dimension of the fiber of the moment map in M2, and the dimension of the fiber in CP3. For an actual toric variety, then over the vertices of the moment polytope, then the pre-image is going to be actually discrete. But here we have something three-dimensional. What happens on the edges? So where one of D1 or D2 is the center of the group. Then we get something, this is I missed the graphic, so. G1, which is in the, one of those is in. And you need there's no constraint involving H1 because G1 is. So this thing is really G, and then this comes from the fact that G2 and H2 commute with each other. So that comes down to P cross G equals to W, and this thing is really all that's left over of conjugation of being able to put the commutator is the ability to conjugate by directional force. So that gives you G cross P, that both of these are two-dimensional. So the dimension of this is 4, and the excess is 2. What about the faces? Those are points where G1 and G2 commute with each other. In this case, these are really the intersection of two conjugacy classes in S3, meaning S2. So 2 copies of S2. That is another basis. Really, all that's missing is that you need to right multiply by oops. You need to right multiply by G2. Each of these things, if the G1 and G2 are fixed, then this is the copy of S2. So you have 2 copies of S2 in S3. Their intersection is going to be S1. Dimensionally.
So the fact that there aren't any interior walls of a genus 2 phenomenon, you get the image of.
Yeah. In higher generi, there would be interior walls. So here you have excess. The excess is 1 because dimension would be 4. And then call it that. So let me write nabla S as the image of the tetrahedron, as the interior of the tetrahedron. So removing the faces, vertices, and edges. And then mu is the moment map, this whole thing that John Weissman values, mapping down to the tetrahedron. That is a moment map for the moment map. But we have to omit the vertices, edges. I'll write mu as the mode map. This is the mode map that I wrote earlier for CP3, and nabla prime as the tetrahedron I wrote for that. So that really is a mode map for an action of U1, Q1. So also restriction. And these must be equal up to an additive constant on the restriction to nabla prime. So that's what we're on the restriction to nabla S. So that's what we're using. Another way of saying it is that both moment maps provide a system of action angle variables. So there is a bijective map from the pre-image of the interior to the pre-image of the interior. Remind you that in higher genera, these spaces are almost always singular because the dimension of the tangent space of the manifold is 2k minus 2 times the dimension of G, which is 6, obviously, which is 3, obviously, so 6k minus 6. That's the dimension of the moduli space, but you have to add the codimension of the image of the F is the commutator map. So it's the codimension of the image of dF plus the dimension of the stabilizer of G and X. So if you're at a central point, then normally this just gives you 6k minus 6, the dimension of the moduli space. But if everything is in the same maximum force, that means both of these things are 1. The dimension of the stabilizer is 1, and if they are all central, then the dimension of the stabilizer is 3. Codimension of the image of the F is 0 unless all of these things are in the same maximum force. So these points should be singular points because the dimension of the tangent space is not the dimension that generic points. And so this corresponds to the vertices. The dimension of the tangent space is 12, not 6. And the dimension, when they're in the same maximal force, the dimension is 8, not 6. So you'd expect these points to be singular points. Narasimhan and Ramanan nonetheless were able to identify the genus 2 moduli space as homomorphic. The dimension of the space where our map is not defined is less than 5 in a subset of G to the 4th of dimension 6. So let's say that we fix G1 and G2 in a maximal force, and let H1 and H2 satisfy equation is the one that I wrote up. Let the H's satisfy that. And if you allow G1 and G2 to vary in dimensional choice, it follows that the space of solutions to that equation has dimension 5. We would be able to quotient this action by the action of G by conjugation, and after that, the dimension of the space where the map is not defined has dimension 4. So, follows that what Eugene, Nanko, and Kwa and I proved is that the set where the map between the moduli space and CP3 is well defined is dense in empty. So, thank you for listening and happy birthday, Bill. He sent me an email this morning. Oh, great.
Are there any other questions for? Okay, we'll come back at 11:30 with Francois. Anyway, thank you again, Lisa.